Inside the Sun, hydrogen atoms are crushed together with such unimaginable force that they fuse into helium, releasing the energy that has kept our solar system lit and warm for 4.5 billion years. Scientists have wanted to recreate that exact process here on Earth for the better part of a century, because if you can trigger it and sustain it, you get a source of energy that produces no carbon emissions, does not depend on the wind blowing or the sun shining, and runs on a fuel so abundant it can be pulled from ordinary seawater. The problem has never really been making that reaction happen. Modern labs can do that in short bursts already. The problem has always been holding it. To fuse on Earth, plasma has to reach temperatures upward of 180 million degrees Fahrenheit, hot enough that no physical material on the planet could touch it and survive for even a fraction of a second. So instead, you have to build an invisible cage made entirely of magnetic fields, strong enough and precise enough to suspend that star-hot plasma in midair without ever letting it touch the reactor walls. In 2026, a Chinese research team announced they had completed testing on a new generation of reactor-scale superconducting magnets built entirely with homegrown technology, capable of doing exactly that. So what does it actually take to build a magnetic cage for a miniature star? And how close does this genuinely bring the world to fusion power? Let's break it down. It helps to understand why magnetic confinement is such a brutally difficult engineering problem in its own right, separate from the physics of fusion itself. The device at the center of China's fusion program is called a Tokamak, a donut-shaped reactor chamber first conceived by Soviet physicists in the 1950s. Inside a Tokamak, powerful magnetic fields are used to bend and trap superheated plasma into a continuous circulating loop, holding it away from any physical surface. The plasma itself is inherently unstable. It wants to wobble, twist, and drift toward the reactor walls, and any single point of contact between that plasma and a solid surface would instantly cool the plasma, halt the fusion reaction, and potentially damage the reactor itself. Keeping the plasma properly confined, stable, and dense enough to sustain fusion all at the same time for longer than a fleeting instant has been one of the central unsolved problems of fusion research for over half a century. Every gain in confinement time, plasma density, or magnetic field strength represents years of incremental engineering progress. This is precisely the arena where China's fusion program has spent the last several years making some of its most closely watched advances. The reactor generating so much of this progress is called the Experimental Advanced Superconducting Tokamak, known as EAST, based at the Hefei Institutes of Physical Science under the Chinese Academy of Sciences, and nicknamed by Chinese media as the Artificial Sun. EAST uses fully superconducting magnetic coils, cooled to nearly absolute zero, around -269 degrees Celsius, to generate the powerful magnetic fields needed to shape and contain its plasma. Operating a fully superconducting tokamak, rather than one that relies on conventional electromagnets, is itself a significant technical achievement, since superconducting coils can sustain far stronger magnetic fields for far longer periods without the enormous energy losses that conventional magnets suffer from. EAST has spent the past several years steadily setting and then breaking its own world records, each new result inching the reactor closer to conditions that would eventually be needed for a genuine, self-sustaining fusion power plant. Rather than one single breakthrough moment, EAST's story has been one of continuous, compounding progress, record after record, each one built directly on the lessons of the one before it. One of EAST's most closely watched achievements has been extending how long it can sustain plasma in what researchers call steady-state high confinement mode, essentially a stable, well-behaved plasma state that closely resembles the conditions a real fusion power plant would need to maintain continuously. In January of 2025, researchers set a new world record by sustaining that stable plasma loop for 1,066 seconds, more than double the reactor's own previous best of 403 seconds, achieved in part by doubling the power of the reactor's internal heating system. That is nearly 18 minutes of continuously confined plasma, hotter than the sun's own core, held stable inside a magnetic cage on Earth. For context on how significant that jump is, fusion researchers around the world have spent decades fighting for improvements measured in mere seconds at a time. A team achieving that same milestone described it as the product of 22 separate rounds of physics experiments and an extraordinary 160,000 individual rounds of testing, underscoring just how much iterative, grinding engineering work sits underneath a single headline number like 1,066 seconds. East's progress has not been limited to simply holding plasma longer. In January of 2026, researchers published a separate result in the journal Science Advances, describing how they had pushed East's plasma past something called the Greenwald limit, a long-standing density threshold that fusion physicists had generally believed plasma could not safely exceed without becoming dangerously unstable. Higher plasma density matters enormously for fusion because it means more atoms are packed closely enough together to actually collide and fuse, which in turn lowers the overall energy cost required to sustain the reaction. But conventional wisdom held that pushing density past the Greenwald limit would inevitably destabilize the plasma and end the reaction. The research team, co-led by professors from Huazhong University of Science and Technology, used a specific plasma startup method to access what they describe as a density-free regime, a state where the plasma remained genuinely stable even at densities well beyond that supposed limit. Crossing a threshold that had been treated as a hard physical ceiling for years is exactly the kind of result that reshapes what engineers believe is possible for future reactor designs going forward. The most recent development in this story shifts focus away from East itself and toward the infrastructure being built to support China's next generation of fusion reactors. As part of a national scientific facility called CRAFT, short for Comprehensive Research Facility for Fusion Technology, Chinese researchers completed testing on a set of reactor-scale superconducting magnets, successfully containing plasma at temperatures of 100 million degrees Fahrenheit. This particular test did not involve generating electricity. Instead, it confirmed the successful development of intermediate-scale reactor components, magnets designed to bridge the gap between East's current experimental setup and the larger demonstration reactors China plans to build next. What made this announcement stand out was a specific claim from state researchers that the entire magnet system was 100% Chinese-made, the product of 6 years of dedicated engineering work, 47 separate patents, and 14 new technical standards developed specifically to manufacture every raw material domestically, without relying on a single imported component. It's worth being direct here that independent Western verification of these specific manufacturing claims remains unavailable, which is standard for research announcements of this kind coming out of any national program, not a flaw unique to this one. That detail about domestic manufacturing matters more than it might initially seem, and it connects directly to a much bigger story that has been unfolding across Chinese science and technology over the past several years. Superconducting magnets of this scale and precision have historically required extremely specialized manufacturing capabilities and materials, the kind of advanced industrial supply chain that only a small handful of countries possess. Building an entire generation of reactor-scale magnets without relying on foreign components means China has established a complete sovereign fusion supply chain, from raw materials through final assembly, entirely within its own borders. Beijing has invested at least $6.5 billion in commercial fusion-related projects between 2023 and September of 2025 alone, according to estimates from the Special Competitive Studies Project. A figure that reflects just how seriously the country is treating fusion, not as a distant scientific curiosity, but as a genuine strategic energy priority worth committing enormous sustained capital toward over years rather than single funding cycles. China's fusion ambitions are organized around what officials describe as a three-step national roadmap, and the Kraft Magnet program is designed specifically to feed into the second of those steps. The next major milestone on that roadmap is a reactor called the Burning Plasma Experimental Superconducting Tokamak, slated for completion by the end of 2027, which is intended to demonstrate a self-sustaining burning plasma state, one step further along the path toward an actual working fusion power plant. Beyond its own domestic roadmap, China is also a key member of ITER, the International Thermonuclear Experimental Research Project, a massive multinational collaboration that includes the United States, the European Union, Japan, South Korea, Russia, and other partners. China has taken on more than 9% of ITER's core component development work, with every component it has delivered to the project so far passing the required international assessment standards. That dual track, an aggressive domestic program running in parallel with a serious international collaboration, gives China both a sovereign fusion capability of its own and a direct seat at the table for the world's largest shared fusion research effort. It's important to stay grounded about exactly what has and has not been achieved here, because fusion headlines have a long history of running ahead of the underlying science. None of East's records and none of the Kraft magnet tests have produced net energy, meaning more electricity generated than was put into the system to create and sustain the reaction in the first place. That remains the central unsolved challenge for every fusion program on Earth, not just China's. Sustaining plasma for 18 minutes, or pushing past the Greenwald density limit, or building magnets domestically at reactor scale are all genuinely difficult, meaningful engineering achievements, and they represent real, measurable progress along the path toward a working reactor. But turning any of that into an actual power plant that reliably generates more electricity than it consumes, and does so safely and economically at commercial scale, is still likely a matter of years, and quite possibly decades of further engineering work, even under an optimistic timeline. Every fusion program in the world, including projects in the United States, Europe, and the private sector, faces this same fundamental gap between impressive laboratory results and a functioning commercial power plant. Zoom out, and this steady drumbeat of Chinese fusion records fits into the same broader pattern showing up across multiple areas of Chinese science and engineering throughout 2026. Sustained, well-funded, incremental progress that compounds year over year until it adds up to a genuinely significant lead in a specific technical domain. Fusion energy, if it is ever achieved at commercial scale, would represent one of the most transformative technologies in human history, an essentially limitless, carbon-free energy source capable of reshaping global energy security, geopolitics, and economics all at once. Whichever nation or coalition gets there first will hold an enormous strategic advantage for decades afterward. China's combination of a serious domestic roadmap, deep and sustained government investment, a track record of steadily breaking its own fusion records, and now a fully self-sufficient magnet manufacturing supply chain is exactly why Hefei has become one of the most closely watched research facilities on the planet. Not because any single announcement guarantees success, but because the accumulated pattern of progress is becoming very difficult for rival programs to ignore. So here's the real question worth sitting with. Fusion has been described as the energy source that is always 30 years away. A joke inside the physics community for decades, because that number never seems to actually shrink. Does a steady, well-funded, methodical program like this one, breaking incremental records year after year while building an entirely self-sufficient supply chain behind it, change that timeline in any meaningful way? Or is this simply the latest chapter in a race that may still take generations to finish? Let me know what you think in the comments. And if you want more grounded breakdowns of the real energy and material science breakthroughs quietly reshaping the future, subscribe. Because China's next fusion milestone, the burning plasma reactor, is already scheduled for the end of 2027.